All right. Hello, everybody. Welcome back after Thanksgiving. Hope you guys had a nice, relaxing time with your family um, and are ready to move forward here in our final 3 weeks of the fall semester. Almost there. Okay, so we are moving on with Unit 3. This is the last topic we're going to include on the summative, which will take place on Friday. This is topic 5, which is on the kinetic molecular theory. And part of this we've already sort of talked about, and you'll see what I mean here in just a minute. So this topic is mainly focused on the assumptions that we make about gases, ideal gases. We're going to bring in some new information on velocities of particles. And we're going to take a look at these things called Maxwell-Boltzmann distributions. Okay, all in all, this is pretty simple, not too complicated. The calculations that I'm going to have you do a few of in the homework, I don't think they're going to pop up, like a lot on the AP exam. What's going to be more important is sort of understanding what these Maxwell-Boltzmann distributions look like and how they can sort of fluctuate based on a few different parameters, namely the temperature and the mass of gases. Anyway, so we'll get to that in time. All right, so we're going to talk about the kinetic molecular theory, some of the things that we already know, and then some of the new stuff. The meaning of temperature, this idea of a root mean square velocity, we'll talk about that briefly. And then I'm going to sort of introduce you to these distribution diagrams, Maxwell-Boltzmann distribution diagrams. But we're going to get more into this in class. Okay, so there's not going to be a separate video. We're just going to do some work with this on Tuesday in class. Okay? All right, so this is a lot of text. I'm not going to go through all of this. I'm not going to read every single word of this to you. This is just from the textbook. This is what the kinetic molecular theory is. Okay? It's a series of assumptions that we make about ideal gases, or about gases that would make them ideal. And a few of these we've already touched on. Okay, so like the first one, particles of a gas are so small compared to the distances between them that the volume of the particles can be assumed to be negligible. Okay, remember that was one of the things we talked about when you have an assumption for an ideal gas, the volume of the particles we can assume to be 0. Never perfectly true, but for the most part it is mostly true. Okay, second one here, the particles are in constant motion. Okay, the collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. All right, I don't see any big issues there. I'm going to talk a little bit more about that in just a minute. The particles are assumed to exert no forces on each other. They are assumed to neither attract nor repel each other. We talked about that one. Okay, remember one of the other assumptions that we had with an ideal gas, we have to assume that there are no intermolecular forces at play. The particles exert no forces on each other. That's one of the assumptions. Okay, and then this fourth thing, and this is going to sort of be the main focus of today, the average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of the gas. And this definitely holds true for the most part. We're going to be talking a lot about kinetic energy, velocity, temperature today. Okay, so this fourth one here is mainly the focus for today. All right, I did want to talk a little bit about the second bullet point there, just briefly, because when I read this, I sort of had a question, and I thought I would just think it out loud. So the second bullet point there from that last page was the particles are in constant motion. That's one of the assumptions in the kinetic molecular theory. The collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. And that word container sort of made me stop and think, right? The collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. So that made me ask, or that made me think, what if there is no container? Is there still a pressure? Right? My first thought was like outer space, right? There's not really a container, right? It's just sort of empty space. Is there still pressure there? Or not even outer space. What about just like the sky, right? just the big wide open blue sky. There's no container there, but there is obviously still pressure. So like, how does that work, right? And I wanted to bring up this diagram here of a barometer, okay, to sort of show you how even if there is no container necessarily, you can still measure pressure. And in fact, the device that we use to measure pressure, which is a barometer, is kind of like a container. So the way that a barometer measures atmospheric pressure is by having mercury, okay, that's a liquid here that's in this container. There's this tube, and the particles, the atmospheric air particles, push down, okay, they exert a pressure on the surface of this liquid, causing it to rise up the tube. And it's the difference then in distance from here to here, okay, this distance, that is measured in millimeters of mercury, okay, and this is a pressure, okay, right? Remember, millimeters of mercury is like an actual unit of pressure. This is one way that we measure pressure. It's like the conventional way of measuring pressure on Earth. It's called a barometer, okay? What I wanted to talk about was like, what's the container in this situation? And the container would be like, this is the wall right here. The surface of this liquid, that's the wall. That's where the particles are colliding and exerting their pressure. It's on this surface, right? They're literally pushing down the liquid and causing it to rise up this cylinder. If there was less pressure, they wouldn't be pushing as hard. This surface could rise up, and this level would go down, resulting in a lower pressure value. If the pressure was higher, then the particles would be able to force the liquid further down, pushing more liquid up, right? And we'd have an even greater distance, and so we'd have an even greater pressure value. So I just thought that would be something useful to think about. Not really related to anything else in this particular topic, but it's just something I thought of, and I thought that maybe you could use a little bit more explanation on. Okay, so anyways, let's move forward here with sort of the remainder of the topic, which is really sort of all about temperature. So the fourth bullet point in that kinetic molecular theory, the set of assumptions, says that the average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of the gas. Okay, so the Kelvin temperature is directly proportional to the average kinetic energy of a collection of gas particles. Well, let's think about any one particle. Okay, any one particle is going to have a mass. Okay, probably pretty small, right? Not a very large mass, but it is going to have mass, and it's going to have some sort of velocity, right? Well, you can calculate the kinetic energy of a object using this equation. Okay, kinetic energy is equal to 1/2 times mass times velocity squared. Okay, you'll learn this in physics if you haven't already. Okay, this is how you calculate kinetic energy, the energy of motion of a particle. What we're learning here is that the Kelvin temperature of a gas is just it's just a measure of the average amount of motion amongst the particles of the gas. Okay, and so that's really just the concept I need you to sort of ingrain in your brains, is that the hotter something is, the more motion there is, okay, in amongst the particles that make up that substance. The cooler something is, the less motion there is. I think it's really interesting. When you go outside on a really warm day versus going outside on a really cold day, why is it hot and why is it cold, right? Let's pretend the sun is not a factor. Okay, so let's pretend it's nighttime. But in the summer, right, you can go out and it can be 70 degrees, right? Maybe even hotter at night, 75. And that feels vastly different than going out, say, last night when it was closer to freezing, right? 32 degrees. What is exactly making the temperature difference there, right? Like what makes us feel that temperature difference? Like what's going on there? And it is entirely related to the kinetic energy of the particles that make up the air. The particles, when they are at a higher temperature, they have more kinetic energy, meaning they're literally moving faster, okay? Because the mass of the particles is not changing, right? The air is made of nitrogen, oxygen. Those masses are pretty much set in stone, right? So the only thing that can really be changing here is the velocity. So if something is hotter, it's going to have more velocity. When those particles, let's say you're talking about the summer night, when those particles hit your skin, okay, they are transferring more kinetic energy to you when they collide with you than cold particles, right? The cold particles are moving slower. They're not exerting as much energy or transferring as much energy to you. That's literally what you are feeling on your skin. When you go outside and it's a hot summer night and you stick your hand out, short sleeve, and you sort of feel warm, what you're feeling is the transfer of energy of gas particles into your skin, right? And when you go outside and you feel that it's cold, what you are feeling is the lack, right? The lack of energy, right? It's so much less than what you might be used to, right? Sitting inside, the gas particles are moving so much slower. They're just not able to really give you any sort of energy transfer, right? And in fact, I mean, the energy transfer is going the opposite way, right? You're warmer than the outside in that case. So, just, you need to have a good idea of what temperature means, okay? And really, this is what it means, right? It's just an average. It's a measure of the average amount of motion amongst the particles in that material or in that gas. Okay, so how do you quantify this? How do we measure this or get some sort of number? The concept that's used is called a root mean square velocity. I don't know why this is the way that they do it. It is what it is. I guess it turns out to be some nice little equation here. But before I get ahead of myself, knowing or calculating the velocity of a single particle isn't very useful, right? Who cares what the velocity of a single particle is? That's not really all that useful. Instead, an average velocity of all of the particles, that would be more useful, right? And so this is referred to as the root mean square velocity of particles. And there's some equations and some derivation in the chapter. It's on page 194. They go through and do some deriving, some fancy math that you don't need to know, basically, that arrives at this equation here. The root mean square, RMS, velocity, okay, that's what this is a letter U for some reason, that stands for the root mean square velocity, is equal to the square root of 3RT over M. Okay? These variables are, right, R is the gas constant, we're used to that one. T is temperature, and M is the mass of 1 mole of the gas in question, aka the molar mass, right? Grams per mole or kilograms per mole. We're going to see in class how the units actually work out here. And you can take a look for yourself right now if you're curious. There's an example of a calculation using this on page 195. Okay, so we will do a few problems working with this in class. Once again, though, like I said before, actually the calculations themselves are not super prevalent on the AP exam. What's more important is sort of understanding the relationships and being able to work with these Maxwell-Boltzmann distributions, which we're going to look at in just a second. Okay, so like I said, relationships. So based on this equation, there are two factors, right, that can influence the velocity of the particles of a gas: temperature and molar mass, right? Remember that R is a constant, right? And 3 is also a constant. It's just a number, okay? So the only two factors here that can influence the velocity are the temperature and the mass, or the molar mass, okay? And it's pretty simple, right? We kind of did some things like this with Coulomb's law, right? The hotter a gas is, the higher the velocity, okay, or the average velocity. It doesn't mean that the velocity of every particle is going to be higher, but the average velocity is going to be higher if the temperature of a gas is higher. And inversely, okay, the heavier a gas is, right, so this denominator term, if the mass is higher, that's actually going to cause our velocity to go down, right? If the denominator term is higher, that's going to cause our velocity to go down. And that makes sense, right? You have heavier particles, they're not going to move as fast, right? So that's kind of intuitive, not anything crazy there. All of this information here, sort of what this equation tells us can be graphically represented in what is called a Maxwell-Boltzmann distribution. Okay, and we're going to play around. I've got a pretty cool little app thing that's on Desmos that we're going to look at in class, where we can play around with some of these graphs. I'll show you that on Tuesday. But just to run you through it really quickly, this is what these distributions look like. It's a plot of particle velocities. Okay. And the y-axis, as you can see here, is the relative number of particles. Remember when we talked about, mass spectroscopy, the relative number of particles hitting at any different mass? It's kind of the same type of plot. The y-axis is the relative number of particles at any given velocity. Okay, so this is sort of mapping out how many particles are moving how fast. Okay, and so like the peak is where you have like the most particles, right? So this sort of purple peak here, this is for nitrogen gas at 273 Kelvin. Looks like the sort of average, or the majority of the particles here are moving, somewhere between 0 and 1,000 meters per second. Whereas, if you heat that gas up to 2,273 Kelvin, the average velocity is much higher, right? And sort of the range of velocities is more broad. Okay, you can see that the hotter the gas is, the faster the particles are able to get, but you're still going to have some that are slow. Okay, and so that's this Maxwell-Boltzmann distribution sort of just graphically represents what the velocities of the particles are really look like. And we're just going to need to be able to sort of work with these plots, answer questions about them, not necessarily do any sort of nitty-gritty calculations, but just, like I said before, sort of understand the relationships between temperature, molar mass, and the velocity. Okay, it's really not that bad. So I think once we have a chance to talk about it in class, it should feel pretty good. Okay, and like I said, this is sort of going to be the last thing that gets assessed on the summative, which will be coming up on Friday of this week. Okay, all right, well, that's it for today. I'll see you guys on Tuesday.